This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Of mass dm, and then I'm going to sum over all of those elements of masses. And the right-hand side, which was this term up here, that's order d to the fourth. Now, what is A cross B, R cross F? You need to know this like the back of your hand. So A is A cross B by definition. Well, you can work it out by writing down the matrix, and we'll do that in a minute. But I want to introduce you to the idea that it's epsilon ijk times ai bj. Now that's very significant because epsilon ijk is like the Kronecker delta, delta ij, which you've already seen, which has this strange property that it's 0 if I is not equal to j, and it's 1 if equal to j. What about epsilon ijk? It's called the cyclic tensor or the alternating tensor, and it's very simple. It's equal to 0 always if I is equal to j. So think of I, j, and k as 1, 2, and 3. And each one of them changes from 1, 2, or 3. So if it's 0, if I is equal to j, I is equal to k, or j is equal to k. So if any one of them is the same as any other one, it's automatically 0. However, it's plus 1 if I, j, and k are cyclic. That is to say, they increase like 1, 2, 3. But it's minus 1 if they're non-cyclic. So if it goes 2, 1, 3, that's non-cyclic. It's going the other direction. It would be going back this way. So if it's cyclic, it's going this way, and if it's anti-cyclic, it's going the other way. 1, 2, 3. So draw a circle. That's what I like to do. And here's 1, and here's 2, and here's 3, and that's cyclic. And if I go back the other way, 1, 3, 2, it's anti-cyclic. Or I go back 2, 1, 3, it's anti-cyclic. So why is A, which is A cross B, this quantity here? So we need to remind ourselves that if the suffix is repeated, then you have to sum it. So supposing I was interested in the k component of this vector A, the k component, one of them. So let's call it AK. All right, so I'm going to hold k fixed. That's going to be 3. And now I can't be 3. It could be 2 or it could be 1. And j can be 2 or 1. But they can't be both 2 or both 1. So if it's 1, 2, 3, it's cyclic. And so I would get A1, B2. If it's anti-cyclic, 2, 1, 3, then it would be minus A2, B1. And so A3, the third component of that cross vector, sorry, infinitely frustrating. So A3 is A1B2 minus A2B1. Well, if you just do what you normally do to work out a matrix, the kth component is A1B2 minus A2B1. And if you put them all in, you can see that that's correct. So the reason for doing that is that I want to replace those R cross U's by epsilon ijk ai bj. So R cross So we're now going to work out the right-hand side, the torque. So what is the torque? It's R cross pi plus R cross F. So let's do that. So if I wanted to work out the kth component, it'd be epsilon ij, and it'd be Ri pi j on the surface n. So it's the force in the jth direction, plus epsilon ijk Rifj, which is from the R cross F. All right. Now, this thing here is going to be dV, which is d cubed, and then another r, which is the size of this small volume. So that's order d to the fourth is this term here. What about this term here? Well, the first thing I want to do is replace pi, pi j, so j is the force and n is the normal, and when I replace that by, you've seen me do it before, I wrote that pi ij, or no, I didn't write that, pi ij nk, pi ki is what I wrote, nk, and that's equal to pi I n. So my pi j on n will be equal to pi, and I can't use k again because I've got k here, so I have to have another suffix, and it'll be pi l j in L. Pi Lj in L. So I've replaced that by that. All right. Now, just to do something simple here, I want to notice that I can use Gauss's theorem, but before I do that, I'm going to replace R, so it'll be a little easier when I use Gauss's theorem, by x. So the distance r from the origin is the same as the vector x, y, and z, so xi. So now, this quantity here times NL, I can replace by Gauss's theorem, and I'd get ddxl of xi, which is this term here, pi lj dv. And why do I do that? This is all a bit tedious, but I just want to make it clear for you because you'll see it done in different ways, but this is the most fundamental way to do it. This is what I remember. So I've got epsilon ijk. Now, if I take, I've got an L here and here, so I have to sum it. So let me sum it. So if L, let me first take the derivative of the first one here. If I take the derivative of this thing here, I'll get two terms. I have to differentiate this, but if I is not equal to L, I get 0. If this is d dx and this is y, I'm going to get 0, right? So the only time I'm going to get something here is when L is equal to I. So I get, when I differentiate this, I get pi ij plus now xi ddxl of pi lj. This thing, these pi lj are just a bunch of numbers. They're a bunch of numbers. So you don't get the force that's acting until you put in the n, like I did here. So this thing is going to, this is a bunch of numbers. It could be large scale. If the derivative is, you know, if the force varies slowly over the area, then this could be quite large. But this is order d cubed, and this is the size of the volume, so this term is order d to the fourth. And my right-hand side are these fluxes of momentum, and they're also order d to the fourth. But this term here, this is a bunch of numbers, and this is either 0 or 1. So this is order d cubed. So this is much larger than that as I shrink the volume. So as I shrink the volume as d goes to 0, this first term here must be 0. And you say, good God, how can it be 0? Well, it could only be 0 because so it requires that epsilon ijk pi ij must be 0. That's remarkable. Why is it 0? Well, because let's take the kth component, let's make it 3. It's telling you that I is 1 or 2 and j is 2 or 1. And one of them is cyclic and the other is anticyclic. So that if I get pi 1, 2, that would be positive, and pi 2, 1 would be negative. So if I add them up, I'll have, so I've done that for you. Pi 1, 2 minus pi 2, 1 is equal to 0. And I could do that for the 3 k's, and it says that pi ij is equal to pi ji. So that's a symmetric tensor, a consequence only of angular momentum, a consequence of angular momentum. Now, I want to just say a word because it's actually useful. The integral form is very useful for applications and also for physical insight, and I want to tell you why. Let's take the teacup, and I've stirred my tea, and I'm stirring it around here with a spoon, right? So, and then I take the spoon out, and to my astonishment, all the tea leaves are in the center. And you say, well, why? So here is what happens. Here is the angular velocity of the tea in the cup, and here's the axis that I'm going to consider when I'm taking moments. And so Blind Freddy can tell you what is the direction of the torque that's being exerted by the solid wall. Well, it's going to be in the opposite direction of it's going to slow the fluid down, right? So the torque is minus Tk. That's the torque that's acting on this control volume. So here's my little control volume, here and here. Well, the first thing you can say, I have to have, if it were steady flow, let's just take a very short period of time where essentially it's not slowing down very fast. So it's essentially a steady flow. It must be true that there's a net flux of angular momentum out if there's a torque. It must be true. So how do I work out what is the direction of the flux of angular momentum? So that's what I have to work out. So let me suppose, to begin with, that because I observe that the tea leaves are here, I suspect that what's happening is that there's a secondary flow that comes in here and goes out the axis. I suspect that. What are the consequences of that? Let me work it out for you. So, I want to work out the flux of angular momentum out of the volume. That's what I have to work out. So here I've got a mass flux across the surface, but the normal that gives the, whether it's plus or minus, is in this direction. If I chose the velocity to be this way, it's going to be a minus. And it's a minus m dot. Now I have to work out r cross u. Well, you would know that that's the moment about the origin. But if I want the moment in the x direction, it's simply r, this distance r, times the angular velocity, times the velocity. That's the moment of the momentum of the fluid, r theta, r u theta. So I've, coming in here, that moment r cross u is going to be r1 u theta 1. Obvious. And what about coming out here? Well, I have a mass flux coming out of here. That mass flux is m2. It's in the same direction as the normal, so it's plus m2. And the moment is going to be r u theta 2. All right, so that should be the moment. That's the net flux of angular momentum out, and that's got to be equal to the torque. So that quantity has to be negative for the way I've drawn it. Well, I wonder if it is. All right, so what is m1? Well, it's rho v times some average area, some average velocity over the area. So the fluid's coming in here. So there's some vertical velocity, I don't know what it is, and there's some positive velocity here, rho v2. So m1 is rho v1a1, and m2 is rho v2a2 of that order. But I know from conservation of mass, this is steady flow, the density is not changing, the net mass flux out has to be 0. So that means that because of this is a u dot n, I'll have a minus m1 plus m2 has to be 0. So it's telling you the obvious that m1 is equal to m2. Must be true by conservation of mass. You can't have any mass out that's different from the mass coming in without the mass in the volume changing. Right. So now I'll put that into my equation up here. So I've just written down the obvious. Now, what about some measure of u theta? How fast is this fluid going around? Well, if I was stirring it with a spoon, it'd be almost in solid body rotation. Almost in solid body rotation. In which case, u theta would be r times the angular velocity omega, omega 1. And u theta 2 would be r times the angular velocity for 2, and those two are about the same. So if I put that into my equation up here for u theta and u theta 2, I'll have an r1 omega squared 1 and a minus because of the minus, and a plus r2 omega 2. So it must be true that this is bigger than that. And if omega were the same, it is. R1 is much bigger than R2. So if R1 squared omega 1 is greater than R2 squared omega 2, then this object inside here times k is negative. But it has to be. It has to be. So if I had drawn my arrows in the opposite direction, I'd have got the wrong answer. The flux of angular momentum would have been positive and not negative. But the torque, we know, is minus tk. So I must have had some idea what I was going to get. But I got the right answer. So this is an example of something that nobody can talk you out of, something as elementary as this. You should be able to make this kind of argument. Standing on your hands. You should know these integral forms of the conservation laws so well that nobody, you're sitting around a table and a whole bunch of people are telling you, well, I don't know what happened, I don't know what happened, I don't know what happened. And you put up your hand and say, I know what happened. That takes courage. There's a lot of people who will sit in their place and never raise their hand for anything. All right. So let's talk about a summary now. Where have I been? And so the integral forms are critical. And what are they? I've written them here in several lines. Oh, good God.
Hey Gary, see in the bottom right-hand corner this little cross?
Yes. Thank you. All right. So here's the integral forms, which are always true, whether the objects are differentiable or not. It says the rate of change of mass, momentum, energy, angular momentum in a fixed volume plus the net flux out of a fixed volume is equal to, in the case of mass, it's 0. In the case of body forces, it's the net force applied. And in the case of energy, it's the heat supplied minus the rate of work done by, or the rate of heat supplied, I should have said, minus the rate of work done by the particles in the volume. And the last one, the angular momentum, it's the net torque applied. That's always true. So I've then written them down for you just to remind you. The first one says the rate of change of mass in the volume plus the net flux out of mass is equal to 0. The next one is the rate of change of a component of the momentum, rho ui dv, times the net flux of rho ui out. Here's the mass flux, and here is its velocity ui across the surface, ds, integrated over that. And that's the net force on the boundary in the ith direction, and the net body force in the ith direction. In the ith direction, because this is the ith component of momentum. And then we had the energy equation, which was that the rate of change of rho e plus a half ui squared, and I showed you how to put the potential energy in there yesterday, even if you're saying that the potential, this conservative force, doesn't change with time. The potential doesn't change with time. So then we could put that in there as an energy term, plus h plus a half ui squared. So this is the enthalpy and the kinetic energy and the potential energy. Rho u dot n is the mass flux, and that's equal then to the rate of heat supplied, q dot, minus the rate of shaft work done, both of which might be 0 unless we're talking about a gas turbine. And then, because we'd included the pressure work that had been done, we included that in here. That's why this is different from this, because we had it in here as E, but we had the pressure times P minus P delta Ki ui, and that led to us being able to write outside of the rho uk nk p e plus p on rho. So that was that, and then this is the rate of work done by the viscous stresses on the volume, tau ki ui nk. All right. So now, quite often, the rate of work done by the viscous stresses on the control volume boundary is often 0 because u is 0. For example, if the surface is not moving, then u is identically 0. So there's no work done by the viscous stress on the boundary. Because u is 0, or you've made the assumption that tau is 0, or, for example, if it's viscous, we're in a region where du dx is 0 on the boundary. I showed you that yesterday. Or the Reynolds number is very large and the viscous work done is negligible compared with the pressure work done. So there are the possibilities for ignoring this last term on the right-hand side. And we're going to do that in a minute. Yes?
Can you please repeat the last case, du dx equals 0? When is that?
If I'm on the surface and I'm talking about tau yx, for example, So you remember that pi ki, this was the direction of the force. And this was the direction of the normal. So the only stress that I've got on the wall is tau yx, typically. Or I could have a tau zx. As direction of the normal, yes, tau z, force in the x direction. So the force in the x direction, and here's the normal, and so the force is acting that way and then so on this way. Tau yx is a number. Multiplied by nk, and I get the force. So the force, here's this is negative, and tau yx times ny is obviously this direction, and this one is this direction. Now, on the surface, right here, u equals naught, ux equals naught. And so there's no work done by the viscous stress on the boundary. Right? So that's what it's all about. All right. I'm glad you asked. Right. So now you've seen me do it many times. I wrote down those integrals and I used Gauss's theorem to put all the terms as an integral over the volume, put them all on the left-hand side and integrated it over the volume. And if the argument, if the integrand is not identically zero, I could choose a volume where it was not. And therefore the integral form wouldn't hold. And so that means that the differential form must hold unless I can't take derivatives, unless the functions are not continuous. So the differential forms of those equations are all of the same. Mass is d rho dt plus the divergence of rho u is equal to naught. Momentum is d dt of rho ui plus d dxk of rho ui uk minus pi ki equals rho fi, and the energy. d dt of rho e plus a half ui squared, and here I've written it because I've not changed the e to the enthalpy, because I've kept the pi ki and not reduced it from with the pressure. So I have d dxk of rho into e plus a half ui squared uk minus pi ki plus qk is equal to rho fi ui. And lastly, the angular momentum equation, you've seen that all that does for you is prove that pi ki, or tau yx, is tau xy. And so in very simple form, here's how I remember it in my head. I have a density and I have a flux, and the right-hand side is a source. And just as it is for the conservation of charge in electromagnetic theory, I have rho is the density and the flux is rho u. And then for the flux of momentum, I have rho ui uk minus pi ki, and the source is rho fi. And the energy is rho e plus a half ui squared, and then this one is rho e plus a half ui squared uk minus pi ki ui plus qk. That is the very basics. Now I want to, they're always true. That's always true. Now I want to do some simplifying for you, because we're going to do compressible one-dimensional gas dynamics. But once you know the basics, the rest is going to be easy. So we can do the rest very quickly. But you have to know the basics. At least I think so. So alternative forms of the equations of motion. So let's talk firstly about the equations for an ideal fluid. So an ideal fluid has zero viscosity, so tau Ki is equal to 0 by definition. And therefore, this stress tensor has only one component, minus P delta Ki, right? The pressure. It has zero thermal conductivity by definition, this ideal fluid. Qk is therefore, there's no heat transferred between elements of the fluid. Qk, the thermal conductivity is identically 0. Now that's frequently a good approximation. Frequently a good approximation. Not always, but frequently. All right, so what can you deduce? We might expect in this very elaborate special case that a particle of mass delta m, and following that particle, if I followed that particle, its entropy wouldn't change because there are no currents. There's no heat and there's no viscous currents. No diffusion of vorticity as we've seen. All right. So this is what you might expect. Let's actually work it out. So what is ds dt following a particle? So I'm just going to use standard differentiation. So I'm going to work out ds dt, and that's the special derivative, meaning the derivative following the particle. So that's going to be the limit as delta t goes to 0 of s at t plus delta t, x plus delta x, y plus delta y, z plus delta z, minus s at t, x, y, and z, divided by delta t. That's what I mean. And delta x is special. Delta x is going to be equal to u delta t. The particle has a velocity in the x direction, u, so in a time delta t, it moves only u delta t. That's delta x. So what is delta y? It's v delta t. And delta z is w delta t. Not more complicated than that. Put those in here. So now we're going to, I'm not going to do partial derivatives for you, but you will know from, I hope, mathematics that this would be ds dt delta t divided by delta t, so that's the partial derivative of s with respect to t. The partial derivative of s with respect to x times delta x divided by delta t, plus the partial derivative with respect to y, delta y divided by delta t, plus the partial of s with respect to z, delta z divided by delta t. But I've just written there for you what this special, following a particle, there's a special delta x. It's u delta t. So if I write in here u delta t, and this is the limit, by the way, as delta t goes to 0, and there are higher order terms, order delta t squared, and so on. But they all go to 0 when I divide by delta t, and the only terms that are not 0 are what is left. Well, delta x is u delta t, so this is u ds dx plus v ds dy plus w ds dz. So following a particle, it's ds dt plus uk ds dxk. And what does that mean? That's the same thing as ds dt plus u dot grad. That's what uk ddxk is. It's u dot grad times s. And that's equal to 0. That's what we suspect. Or we could do it another way. we could say, all right, following a particle, I'm expecting that ddt, so rho dv is the mass dm, and I've got s per unit mass. So this is summing up over this volume of particles, their entropy. And I suspect that's going to be 0. Do I get the same answer as what I've just worked out? I hope so. I hope so. But what that is, this is a moving volume, but I've replaced it, and you've seen me do it 1,000 times now. That's ddt of a fixed volume plus the net flux out. All right. So now, this net flux, we're going to use Gauss's theorem for that. And that's going to give us a ddxk of rho SUK. That's the divergence of rho SUK. So from Gauss's theorem, because this is arbitrary, the volume is arbitrary, then I automatically can take this ddt inside and it becomes a partial derivative, and I have ddt of rho s plus ddxk of rho SUK equals 0. But that's not the same thing as I just wrote down. Or is it? It is the same because I can now expand this out. So these are products, so let's take S as one of the product terms. And so I have S d rho dt plus S ddxk of rho UK plus rho ds dt plus rho UK ds dxk equals 0. But this is conservation of mass. So that is identically 0. And so I've shown you that even in this case, I get the same answer as I had before. Rho ds dt, rho into ds dt plus u dot grad s equals 0. So so we get the same answer, just as I did before. Now I want to prove to you that that also follows from our basic equations. And this is a bit elaborate, so I hope you can follow it. So I'm going to write down the energy equation. Here it is here, rho into E plus a half ui squared plus ddxk of rho uk into E plus a half ui squared plus p delta ki ui is equal to rho fi ui. So this is because there's no viscous stress in this ideal fluid and no heat conduction. So this is the energy equation. No external work done and so on. All right, so now this term here is the same here. I just didn't write it in. And then ddxk of rho uk plus into E plus a half u squared. Now, what is this here? P delta ki ui. Well, you've seen me do that before. I'm going to sum over I. And the only time I won't get 0 is when I is equal to k for this Kronecker delta. So I will have to be equal to k, in which case I get puk here. And that's equal to rho fi. And now I want to write down the momentum equation in general. The momentum equation for viscous stress is equal to 0 is ddt of rho ui plus ddxk of rho ui uk plus p delta ki is equal to rho fi. I've done that many times. And I've written down the mass for you as well, d rho dt plus ddxk of rho uk equals 0. So now, if I pull out of this term and this term, ui, I'll have d rho dt plus ddxk of ui, ddxk of rho uk. But that's the mass equation. So when I do that, I'm left with the terms that remain, namely rho dui dt plus rho uk dui dxk plus dp dxi. when I take this derivative here of pressure, d dxk, the only time k has to be summed, the only time I'm not going to get 0 is when k is equal to I. So this must mean that this term is dp dxi. All right. So I've subtracted the mass from the momentum equation, and I got this equation. I'm going to do that again for you later. Now let's multiply this equation by ui. And the reason I had to subtract the mass is that I can't multiply this equation easily by ui and get the answer that I want. But this equation I can multiply by ui. So just imagine in your head you're multiplying this equation by ui. So you wrote the equation for u1, and then you multiplied it by u1. And then you wrote the equation for u2, and you multiplied the equation by u2. And the same for u3, and you multiplied it by u3, and then you added them all up. So if I multiply this by ui, I'm going to have rho d dt of a half ui squared. Why? Because when I differentiate this, I get 2 cancels with the 1/2. I get ui to ui dt, which is what I had when I multiplied this by ui. And the same with this one here. I have rho uk d dxk of a half ui squared. And I have here ui dp dxi, and I have rho fi ui. All right. Now we're going to do something a little tricky. We're going to multiply the continuity equation, or the mass equation, d rho dt plus d dxk of rho uk, which we know is equal to 0. We can multiply it by a half ui squared and we'll still have 0. And we'll add it back to this equation. Wait a minute now. Yeah. Yes, so you can see that this is rho d dt of a half ui squared. If I add this one here, I'll have a half ui squared d rho dt. And so this term plus this term is d dt of rho by a half ui squared. And the same will be true for this term by a half ui squared and this term. And I'll have a d dxk of rho uk by a half ui squared. And this ui dp dxi would be the same thing as uk dp dxk, because it's summed. But that's the same thing as d dxk of puk minus p duk dxk. That's the same thing as this term here. So now that's the same thing, but this equation now has a lot in common with the original energy equation, which I wrote down up here. And in fact, you can see that when I subtract one from the other, I'm just using the kinetic energy I got from the momentum equation. I'm just using that to subtract it from the original energy equation. And what do I get? Subtract it from the energy equation, and I'm left with, oh God. You can see I don't know what I'm doing. Oh yeah, I'm nearly there. All right. So I subtract this from the subtract this equation from the original energy equation, and I get rho I get rho dE dt plus UK dE dxk. And now I've been a bit tricky here. I have So so I subtracted, oh yes, I see what I subtracted this equation from the energy equation, and I'm left with ddt of rho e plus ddxk of rho uk e, and this term cancels, and when I subtract this, I get plus rho, p duk dxk equals 0, and this right-hand side goes to 0. Now I'm nearly there. All right, so now I'm going to expand out this equation, take the common factor e out, and so I have e d rho dt plus ddxk of rho uk plus rho de dt plus rho uk de dxk, and plus p duk dxk equals 0. But now I'm going to use yeah. So from the mass equation, I have that d rho dt plus uk d rho dxk is equal to rho duk dxk. That's just expanding out the conservation of mass. And so so this term is 0, and this term is rho de dt plus uk de dxk times rho. That's these two terms. And this term is, I can replace it by the mass equation, and that would be P, and if I divide it by rho, I then have, if I divide this equation by rho, or put this P out here, I need, so this is, this term here is minus this and minus that, and that's where this minus comes from. And I've got P over rho, and I've got a d rho dt plus uk d rho dxk equals 0. So that's very, very pleasing, because you've just seen from what I did for the entropy that this dE dt plus u dot grad u e is the same thing as dE dt following a particle. So this is rho dE dt, and this is d rho dt following a particle, minus p over rho d rho dt equals 0. But now I come back to my thermodynamics and the thermodynamic identity. The thermodynamic identity is that TdS, and these are variables of state, TdS is dE minus pdV. And dV is 1 upon rho, so this is minus 1 upon rho squared d rho. So TdS is dE minus p on rho squared d rho for a fixed particle, for a fixed mass. So if I multiply this equation by rho t, simply by rho, I'll have rho t ds dt following the particle is equal to rho dE dt following the particle minus p over rho d rho dt. But that's the same thing as I just got from my equations of motion. So I can replace all those equations by ds dt equals 0, just as I expected. So I've just proved it for you, that it's the same thing. And that makes a huge difference. You will know that when you do acoustics, you assume in acoustics that the entropy is constant. Why? Why? When will that be a good approximation? When the wavelength is very large and the heat from the compression here takes a long time to diffuse and heat the other half of the wavelength, where the temperature is lower. At very high frequencies, it'll break down. It'll break down. And you can work out what is the number that you need in order for it to break down. It'll depend on the frequency. The higher the frequency, the shorter the wavelength. And so you won't be able to use S equal to constant so accurately. But at very long wavelengths, you can. So for this special ideal fluid that's non-heat conducting, has no viscosity, I can replace all of these elaborate equations by simply one in which ds dt equals 0. That is, in the absence of shocks, discontinuity, the equations of motion for an ideal fluid can be rewritten to give ds dt equal to 0. And we can replace the elaborate energy equation simply by ds dt equals 0. And that's very important in acoustics. So our equations then become d rho dt plus the divergence of rho u, that's conservation of mass, and that gives us 4 unknowns, rho, u1, u2, and u3. And it's one equation and 4 unknowns. The next equation is the momentum equation, which is for each component rho rho ui ddt of that plus ddxk of rho ui uk plus p delta ki equals 0. And there's a new variable now, p, but that's 3 equations because there are 3 components. I is 1, 2, or 3. And then we have ds dt equal to 0, that's one unknown. And lastly, we have an equation of state, which we can get from the canonical equation of state, h of s and p. We can get p is a function of rho and s. And that's gives us one equation. And we now have 4, 5, 6 unknowns and 6 equations. We have a closed system. So there are 6 equations and 6 unknowns. All right. I got to quit very soon. Should I quit already?
3, 4 more minutes.
That's generous. All right, I'll just do the Euler equation for you. What is the Euler equation? The Euler equation assumes inviscid flow, no viscous stress, and no thermal conductivity, so it's an ideal fluid. And we write momentum, ddt of rho ui plus ddxk of rho ui uk plus p delta ki is rho fi. And we're going to subtract continuity. So if we pull ui out of this term here and this term here, we'll have rho dui dt, well, we'll be left with, rho dui dt, because the continuity will cancel those 2 terms. We'll have ui into d rho dt plus ddxk of rho uk, which is 0. So we subtract continuity out of this equation. And of course, when we sum the k's here, the only contribution is when k is equal to I. And so this becomes a plus dp dxi, which I put it on the right-hand side, and the rho fi is on the right-hand side, and that is called Euler's equation. It's an inviscid equation, and it's an exact equation, follows from the momentum and continuity. You can also write it as rho du dt plus u dot grad u, where u can be 1, 2, or 3, this I. And this is minus the gradient of P when you add these three equations up, and this is rho F when you add the three equations up. So the equation can be written like this, or now we've seen from